Hi, this is Lynn Langett. Welcome to part 2 of my 5-part series on understanding Hadoop MapReduce fundamentals. So we've had our brief introduction to Hadoop technologies and seen how to get started with our first development environment. You might be thinking, why is not everyone using this? What's holding people back? This seems like a really kind of an interesting technology. What's the problem, basically? Why aren't people just converting to this new massive scale? And here it is in a nutshell. What the database community wants to do, of course, is leverage all the skills that it knows, particularly the expertise in the SQL, ANSI SQL query language, and to combine that expertise with the massive scalability of Hadoop. So center of the holy grail of this world of Hadoop is to move towards some SQL-like language so that all the knowledge that people have can be applied, but just to more data that's stored at a larger scale. So we'll be covering in quite a lot of detail why this destination is not quite, there's not quite a direct path to it at this point in the Hadoop ecosystem. And the various ways that you can use SQL on Hadoop or SQL-like language on Hadoop, and how you can use it, when you can use it, and when you can't. So to that end, we are actually going to start not with traditional MapReduce, but we're going to start with sort of the current state of affairs and what I see a lot of actual customers trying to use with Hadoop. And that's an abstraction layer called HBase with a query language called Hive. So you can see that there are a number of libraries that you can include in your Hadoop distribution, and these are shown on the left, things like HBase and Hive and Pig and Scoop and Uzi and Mahout and all those sort of funny names, and that accessing the data in the Hadoop file system can be done with a combination of those libraries and various programming languages. I think for many people starting, for myself included, it's confusing because you can basically retrieve the data in almost any language that you can think of, but it's a combination of libraries and languages that is sometimes used. There's different ways to look at it. Most commonly it is Java with traditional MapReduce, but of course not everybody is fluent in Java, nor are they fluent in the MapReduce programming paradigm. We are certainly going to explore that in some great detail, but to be inclusive, I wanted to at least show you one of these abstraction layers that is currently very, very popular. And if after you watch this course, your conclusion is, I want to use Hadoop, but I really don't want to learn MapReduce because it doesn't seem to be the right tool for me, I encourage you to work on learning Hive, because Hive, as we'll see, is similar to ANSI SQL, but not the same. I think it is. That being said, it's also important if you're going to use an abstraction layer that you have some idea of what that abstraction layer is producing, i.e. a MapReduce job. And to do this, we're going to use our sample VM that we set up, our Cloudera CDH4, and we're going to work with a Hive query. In this demonstration, I'm going to use Hadoop on the Cloudera virtual machine running on Linux on my Mac, and I'm going to use some of the included tools to run a Hive QL or a HQL query inside of this virtual machine to get us started working with data on Hadoop. So to do that, I'm going to open the included browser, which is Firefox, and inside of here I'm going to open up their utility called Hue, which is on the bookmark list. So now you'll see that in this Hue utility, which is a local web browser that has this address of 8888 beeswax, this is where this comes from, we have some different utilities here. So we have About Hue, we have beeswax, Hive UI, which is where we are here, where we can, in a GUI window, execute Hive queries, which are SQL-like queries. We have a file browser, we have a job browser, we have a job designer, Hue shell, the admin, questions, and then if there's any alerts. Now underneath beeswax we have the query editor, we have my queries, saved queries, history, tables, and settings. So let's first go over to tables, and you can see that we've got 2 sample tables here that are made available for us. So if we browse data, you can see that we have this sort of weird logged error message, which I'll be explaining in just a minute, and then we have the results. So we have regular sort of data here where we have code, description, total employees, and a salary. And we can download this as a CSV, Excel file, or save it. And then it tells us about the MapReduce jobs that were run to take a look at this, which gives us a hint that this is not relational. And then let's go into query, and this is the query, which looks very, very much like the ANSI SQL that we're used to, but this is, of course, HQL, and then we have a log. So if we wanted to see what was on the file system, we wouldn't go to the file system here. This would be the file system on Linux. And this is a common point of confusion when people first start working with MapReduce. Now, as a point of fact, you can run a MapReduce job pointed to the local file system for testing, and you sometimes do as a developer. But when you're running MapReduce jobs in production, of course, one of the reasons you use MapReduce is because it's parallelizable, and so you'll generally be running it against the HDFS file system. So is there a viewer so you can take a look at that? Yes, there is. There are actually several. So if I look here on the file browser, I can see that I have this directory structure, which looks like the regular file system, but this is the HDFS file system. So if we go inside of here, we can take a look, for example, and we can see what information is available. Now, in addition to this, we have the Hadoop name node utility, which allows us to browse the file system. And you'll see there's the similar thing that we just saw, and we can browse in and we can take a look at the different directories and go all the way down to the location. So again, when you're just getting started, this is a common point of confusion. So there's the regular file system, and then there's HDFS. So HDFS is the file structure that Hadoop is designed to use, that is designed to work with the MapReduce API in terms of retries and distributing the data and so on and so forth. So again, we'll be getting into all those details as we go through the course. At this point, I just want to show you that you can use this Hue tool to run a SQL-like query so we can have a basis for starting, so we can contrast how this is the same as what we're used to in the relational world, and more importantly, how it's different. So if I click on My Queries, you can see that I have a query here run against that table, which was basically just kind of a reference table. So if I go into Options, you can see that I have Edit, Delete, Usage History, or Clone. So if I go ahead and clone this, you can see that that puts this into the query editor. And this looks, a lot like ANSI SQL. And as we go through this course, hopefully you will get the understanding of how this is same and how it's different. Now I can just click Execute. I can save as, Explain, which will tell me how the query is going to be executed, which we may come back to that, but let's go ahead and click Execute. So this took maybe half a minute for this relatively small query, and this is a very, very important difference that we'll be pursuing as we go along. So there's the result, there's the query, and then if we switch to the log, notice MapReduce job launched, job 0, map 2, reduce 1. And a cumulative CPU, HDFS read, so where this is coming from. So then we can go into the query history, and we can see the query history. Now I've switched over to the Wikipedia entry on Apache Hive, because although this course does not cover Hive extensively, I would recommend that you take a deeper look at Hive. So you can see here Hive is a data warehouse infrastructure built on top of Hadoop for providing data summarization, query, and analysis. It was developed by Facebook, and it's used broadly by companies such as Netflix or AWS. So you can see the features of Hive in this overview, and you can see a bit about HiveQL. As it says, while based on SQL, HiveQL does not strictly follow the full SQL 92 standard. Also, HQL does not have support for transactions, materialized views, and doesn't really support subqueries. As you saw in the previous demo, Hive is an ANSI SQL-like language that sits on top of HDFS and generates one or more MapReduce jobs. It's important to understand that the execution process, while familiar in feel, because it's ANSI SQL-like, but not the exact same thing, kicks off batch processes. So Hive was created by some of the early and big users of Hadoop for easier interactive exploration. It's often used with very small subsets of data, kind of as a testing or a trying out, but it is only a part of the Hadoop ecosystem, and it is definitely not a one-for-one replacement for MapReduce. So again, I encourage you to take a look at Hive syntax and Hive limitations, and to think about, when considering Hadoop solutions, the place of Hive, the role of Hive, along with the place of other libraries, languages, and utilities. And just because I want to say it one more time, HQL, or the language that Hive uses, is not equivalent to ANSI SQL. I have, in working with customers and writing and researching, heard this said over and over and over. It feels familiar, but things that we're quite used to, such as our join syntax, works very, very differently. And that really allows me to kind of open the point of thinking of what types of activities MapReduce is good for and not. And as a general rule, joins are not a super great use case, even though this language would look like it would be working just the same way it does in a relational database. So I encourage you to do more exploration around Hive and to get a direct comparison with ANSI SQL. There's lots of charts out there if you're going to take that approach in your HDFS solution. Now let's move into the world of MapReduce with that, I guess, kind of a segue of an introduction. So before we get into the programming of MapReduce, we need to talk about preparation steps that are commonly taken. And because MapReduce is operating on very large amounts of data, we need to talk in a little bit more detail about what considerations you need to have around the data that you're going to be working with on your MapReduce job or jobs. So I'll remind you that the underlying structure of the HDFS file system is very different than the traditional file systems, in that the block sizes are quite a bit larger. The actual block size for your cluster is dependent on the cluster configuration. Currently, the options are 64 or 128 megabytes. So you have to think about where your files are going to be partitioned, and if you need to do any sort of custom partitioning based on those block sizes. Another consideration is where you're going to retrieve your data from in order to perform the MapReduce operations or the parallel processing on it. Although as core Hadoop, you will work with the Hadoop file system, as you'll see in the demos and discussion, it is possible to execute MapReduce algorithms against information stored on different locations, such as the native file system and cloud storage buckets such as Amazon S3 or Windows Azure blobs. So that's an additional consideration. Obviously, if you're going from on-prem to cloud, you have to also think about transport up and down and frequency of synchronization and those kind of considerations. Another consideration is that the output of the MapReduce, the job results, is immutable. So your output is a one-time output, and when a new output is generated, you'll have a new file name. So the final consideration in preparing for MapReduce is thinking about the logic that you'll be writing, and we'll be certainly talking quite a bit more, but just to introduce the topic, you will have, of course, your data input, whatever particular business situation you're trying to address, and then you will be writing logic in some programming language or library or some tool or a combination to map that data to then reduce it, and then you'll have some output. One of the concepts that I want to have you start thinking about is when you're working with the data coming through the MapReduce pipelines, whether it's a single job or multiple jobs, you're going to be working with key value pairs. So irregardless of the format of the data coming in, and as you'll see, it's very commonly expressed as large text files. That's certainly not the only type of information you can bring in. There's many, so virtually unlimited, but it's simplest to understand. So the idea is a large text file, you have words separated by spaces, and then you have line separators as well in some of these text files. You want to output key value pairs. And this can be based on the types that ship with MapReduce, or sometimes you have to create your own types. We're going to start with the types that are available in the library, and then as we get into the advanced section, we'll talk about creating custom types. So you have these 4 considerations when you're starting to plan or prepare for MapReduce. Loading the files, where the data is coming from, where the output will go to. Again, it can go to HDFS, it can go back into the cloud, go into the file system or any other location that you want to put it, and then the business problems that you're trying to address with this framework and how you're going to write your code to address this, and with what languages and tools. So before we get started running our first MapReduce program, because it is most common to see MapReduce examples run on Linux, although in this class we're going to run both on Linux and on Windows. If you, like me, are not as familiar with core Linux, I did include in this slide just a list of common Hadoop shell commands, which are very similar to Linux commands. So again, if you've got a Linux background, you probably can just skip through this. But for those of us coming from Windows, I've found this to be a little bit helpful. So you can see this is just kind of a path through which you'd go when you are executing a MapReduce job that you've already written the logic for, and we'll be having a demo on this coming up. But just to give you kind of a sense of it, so you have the Hadoop file system, and then you have these various commands. Cat allows you to read the contents of a file out to the screen, and the convention, if you're addressing the local file system, is the file : 3//. And then you have file system make a directory, and so you're making directories here in the HDFS file system, and you'll probably remember that you're commonly working between the underlying file system, whether it's Linux or whatever, and the Hadoop file system when you're working with MapReduce. Then the next command there is copy from local, just passing in, you know, the arguments from and to. That you can alternatively use just a put, and that will put a local file, so from the local file system, up onto the HDFS file system. And there are various types of naming conventions. I just gave you an example here with the HDFS : whack whack, and then nnexample.com, so on and so forth. I included also sudo. Sudo was new to me when I first got started with this world. It's roughly equivalent to run as administrator, run as another user, usually the super user. So in some cases it's not required, but I just put it to show you the syntax usage. You'll need to or choose to have a sudo command. So this next command is the jar, which is the compiled Java, the compiled MapReduce, and you pass the jar file, and then you call the method that is to be run when the jar is executed for the MapReduce, and then you say where the input is coming from and where the new output should go to. Then generally what you'll do when the MapReduce job finishes is you run some kind of command to verify the output. So again, the same idea is you can run an ls, which is a list the contents of a directory, and then once you determine the output file name, and it's not called file1, it's, as you'll see, there's an output directory created with multiple files, but I just put file1 to make it simpler here. So the cat command is often run to read the contents. Sometimes you just want to read a portion, and you can do that as well with some various commands, and then you can also run a git. One other tip or note that I put on here is you'll see in the documentation, the second point, some Hadoop configurations use Hadoop DFS rather than Hadoop FS. So what that technically means, and I have a link in the notes, is DFS refers only to HDFS. FS can refer to either file system, the underlying operating system file system, or the Hadoop file system, depending on the paths that are supplied. So I personally tend to use FS, and I'll use that in the examples, but you'll see both, so I wanted to call it out here. So in this next demo, I'm going to show you how to work with files in HDFS. Again, I'll continue on using the Cloudera CDH4 demo VM with Hadoop on Linux, and I'll use a combination of the command line. Also, I will use the included GUI file browser because I found that when I was learning to be a little bit easier than trying to learn Linux command line as well as MapReduce. So I'll include both in the demo. In this demonstration, I'm going to show you a little bit about working with files in the HDFS file system. You can consider this a precursor to setting up your first MapReduce job. So if you're familiar with Linux, you're probably going to skip this demonstration, but I know a lot of my audience isn't, and so I wanted to add it because I found this to be helpful when I'm working with people getting started. So I've got the Cloudera VM, and I've got a couple different ways that I can work with sample files getting ready to process word count. So if you take a look on the desktop here, you do have a Windows Explorer kind of a browser. It doesn't work exactly the same, so it's a little bit tricky when you first work with it. Works similarly though. So I can go into the Cloudera directory, and what I actually did is I made a sample data directory, and you just right click, so that's easy enough to do. And then I made a new sample file, and you're of course going to be using a different kind of text editor here. So if I open that up, it's using, I believe it's the Emacs text editor, so it works a little bit differently. So I just made a little hello world for just simple testing, which is something that I would recommend that you do. In addition, you're probably going to want to download some sample files to play around with. Most of these files are going to come in a compressed format. So I retrieved, for example, the million song subset, which was a gig of data, and it's compressed. So the compression is different here. It's tar.gz, so you're going to have to uncompress it using a Linux command line, and then you'll get something that looks like this. Now you can navigate the file system this way if you want to, but it's really common that when you're working with Hadoop, you will actually work with the terminal window, so similar to the command window in Windows. So I'm going to go ahead and open that up and show you just a couple of commands if you're new to this world like I was. So pwd is present working directory, and then change directory still works the same. So if you want to change directory, and then pwd works that way. So that's kind of a handy thing to know. Another thing you can do is if you want to open a terminal window from a particular location, just like you can in Windows, you can do it that way, and now I'm in that particular directory. If you're wanting to run some activity as administrator, the command for that is sudo or superuser, sudo, so that is a handy thing to know as well. Now we're going to move from the Linux file system into the Hadoop file system, or HDFS, and I'll start by working in the terminal, and then I'm going to use Cloudera's graphical viewer as well, which is also sometimes helpful. So first I'm just going to bring up the commands that are available by typing Hadoop FS. And then you're going to see that we have a list of commands, and I did include in the course materials just a quick reference on some of the ones that I use most frequently, because the most common activity you'll do as a developer is you'll be moving your sample data from the file system into HDFS, and you're probably going to be running in what's called pseudo-distributed mode on your development machine, which means you're going to have a single node, although there's many different flavors that you can do there. So once you are into the Hadoop file system, then what you may want to do is you may want to see what is available. So if you say Hadoop FS, and then you just say ls and user, then this is the first level of the file system, and you can see there we have some different directories. And again, this is an abstraction over the top of the Linux file system. I think what I'm going to do, just to give you a visual on this, is I'm going to go ahead and switch to Cloudera's browser tool, and we'll switch kind of back and forth, because I know when I was learning this was helpful to me, so I'll just share my method of working with this with you. So I'm going to go ahead and bring up the Hadoop name node viewer, and you can see there's a ability here to browse the file system, which I just found to be useful. So you can see user, temp, and the VAR directory. So you can see that we've got the user directories, so on and so forth, shown the same way here. And if I want to browse into them, I can browse into the temp directory. And these are my various permissions, and you can see there I've got some stuff that I was working with in something called beeswax, and I can just go back and forth inside of this viewer as well. So this is a handy thing when you very first get started to verify that when you uploaded data into HDFS, it actually got up there. So I'm going to go ahead and go out of that and go back to the terminal window, and I'm going to just do a couple of show you a couple of things here. So again, I'm going to do Hadoop file system and ls, which is a listing command into the list of directories, and that's going to return a list of directories. And then I'm going to make a directory, which is this mkdir, and I want to make it at the location of user, and I want to call it new lin, and I want to just go ahead and do that. And then if I go ahead and I do my ls, you can see here's my new directory down here. And then if I wanted to move some information into there, then what I could do is into the new lin directory, I could do a couple different things. Copy from local is one way to run your copying your data from your file system into the HDFS file system. You can also do a put command like that, and then if you do that, then you're going to put the file name, and then you're going to put it into HDFS, and the syntax is you need the fully qualified, so the name node, whatever it might be, and it's not example in this case, but and then into the Hadoop directory, and then put it into the directory that way. Now once you have files in the directory, then a quick way to read them is to use the cat command, and that reads the particular file. Now another thing that you can do is you can read from the local file system. So that's the syntax for reading. Of course, obviously the 3 forward slashes are in the directory that you're working in. So if you only want to read a part, you can use the tail command, and then here's just another example. That will read a portion of a file, which is sometimes handy in this particular case. So really that's super fast introduction to the file system commands. Now I tend to use this one of these Cloudera interfaces here. In particular, I tend to use the Hue interface because there is a file browser here that is similar to the one that is sort of standard with Hadoop, but you can see here's the same 3 directories here, and if I say new directory, I can call this lin data, and actually I'm going to do all small letters. Let's call it lin data and say submit, and then that creates this new directory. And then inside of this directory, I can go ahead and upload files, and I can upload a file, and here I'm going to go into my sample data, and I'm going to upload my hello world file, and I just find that to be simpler. So, and then I can go inside of here, but it is important that you understand that this is a viewer against the HDFS file system, and you can see it's viewing the blocks. You may remember from the lecture that the storage here is completely different than the underlying file system. HDFS stores in 64 meg or 128 meg blocks by default, and here they're showing you how much of the block. And you have some other abilities here that are specific to Hadoop: view as binary, edit file, download, view file, so on and so forth. You can see last time that you worked with the file. So again, I find working with the file browser that comes with Cloudera simpler than the command line, but I do see when you're working with the Cloudera distribution, most of the demos assume that you have some knowledge of the terminal, so I wanted to take a few minutes and go over that in this demo as well. Alright, we've spent quite a lot of time in background in this class. Hopefully you've taken the time to go with me through the background because I think it's quite important. But of course the title of this class is Hadoop MapReduce. So the key and core of it for us as programmers is to understand the programming paradigm that MapReduce is. And I'm going to be honest with you, MapReduce is difficult for those of us that come out of the typical object-oriented world of, let's say, Java or C# or VB.NET. And it's a very challenging thing to get your head around. There's no sort of easy way to get it other than to spend quite a lot of time with it and to run example after example after example. So that being said, there are some stepping stones that can help you to get it. And one of the first and most important ones is what's expressed in a couple different ways in this slide. The first thing is take a minute and read the cartoon. And then read on the bottom. and absorb the fact that the programming paradigm is fundamentally different than the one that most of us use every day. And what I mean by that is MapReduce is designed to be written in a functional manner. Now, it can be written using purely functional languages, but I think that's a little bit much for those of us coming out of the C# mostly world. So I'm going to be addressing it mostly in Java because there's not too much difficulty to translate between C# and Java per se, but added to the complexity of translating whatever language that you know into whatever language you'll program with. And it is, by the way, possible to program with C#. The bigger difficulty is understanding the correct method of programming in MapReduce. In this world of huge amounts of data with parallelizable executing jobs, if you do not approach the problem thinking functionally, another way to say this is mathematically. So literally one set of input coming in, one function, one set of output coming out, you are really not going to have success. So if you've got a strong object-oriented background, you're going to either have to just put that aside, clear your head, do some unlearning, something. Because if you're expecting to program in the sort of the familiar fashion, just basically translate your C# into Java, you're heading into dangerous waters. Now, with that daunting introduction, it's time for us to get into some of the technical details that will lead up to our first demo where we can see the actual code and see the MapReduce running. So as I mentioned earlier in the lecture, the idea is that you get some sort of input and that you will then generate through your processes a set of key value pairs. And in reality that becomes multiple sets which can change throughout the course of a job run. So the first portion of the MapReduce is the set of map phases or the mappers. So this is one of the methods that is key and core to running MapReduce and something that's very important you can effectively write. Now we're going to look at this from two aspects. We're going to look at it kind of from a basic aspect, and then we're going to come back around and look at optimizations. And I know my audience, programmers being programmers, you'll want to be doing optimizing from really this slide on. But I'm going to ask you to bear with me so that you can understand the core programming paradigm first, and then we'll layer on optimization second. So in the map phase, which literally is expressed as a map method, there is a set of information coming in which is physically stored on the separate nodes across the cluster, and then the mapping method will generate a set of key value pairs on each node that is determined by the logic of the map along with other aspects of the map such as the input split. In other words, how the information will be split. This will be output as a list of key and value pairs. There will be one list per local node. Now you can implement additional processing on that node, very commonly done. One of the most common things is something called a local reducer or a combiner. In the next step of a MapReduce job, the MapReduce algorithm itself performs what's called a shuffle and sort. And many people call this the secret sauce or the magic of MapReduce. The shuffle and sort phase is designed to be as automatic as is possible, in that your mapped output will be then sent to the appropriate nodes for further processing, most commonly aggregation. As in any phase in the MapReduce pipeline, you can of course tune this. And in the last part of the MapReduce pipeline, the method that you write around reducing, which as I mentioned commonly does aggregation, is performed on the output from each of the mapper nodes. So you have a key and a list of values. The shuffle and sort phase will precede it, and it will combine the map output into a list, which will be the final output. For those of us who like to see things in more of a pipeline, across the bottom of this screen I have shown you the pipeline of the key value pairs. So the input, a key value, then the map, then the output, then combining, and then reducing, and then the output. So that we can deepen our understanding, let's look at the hello world of Hadoop, which is called word count. We have input, which, as I mentioned, is often a bunch of free-form text or text from a book or something. And then we have a splitting process when we load the information onto the various map nodes. And you'll remember from earlier discussion that although a single map node is shown, Hadoop includes built-in redundancy. So by default, this data will actually be copied to 3 physical nodes. This can be, of course, adjusted like anything else via configuration settings or job settings on the MapReduce pipeline, but the default is 3. The diagram here only shows 1. Then during the mapping phase of the job, the information on each node is processed to produce a set of key value pairs. So in this case, it's just separating the words on each space and then putting in a 1 for the count of the word. Then comes the shuffle and sort phase, which is performed automatically by default. And then the resulting reduce phase performs, in this case, an aggregation or a count of each of the words and produces a final result set, which you might remember is immutable. Again, to help us map the logical implementation back onto the physical implementation, which is important when we're programming this up, I'll remind you that by default, you will have separate physical machines that have separate daemons or services on them. Each daemon is its own JVM. So you'll have at least one master node physical machine, which will have the name node service and the job tracker service. This will then communicate with n number of slave nodes, each of which will have task tracker daemons to process the individual map tasks, for example, and possibly reduce tasks. And they will also have data nodes, which communicate back with the name node in terms of mapping. Now, this is a very oversimplified drawing. Of course, it's very, very common that rather than 3 slave nodes, you'll have 10 or 100 or 1,000 or even more slave nodes. That's a reason to use Hadoop, that it is scalable to huge, huge implementations, terabytes or petabytes, which can be hundreds or even thousands of slave nodes. Again, programmatically though, it's important to remember that each of these JVMs for the daemons do not share state. They are separate. This is an important point when we're thinking about the functional paradigm that I talked about when I introduced MapReduce programming. As I said earlier, there are a number of libraries and languages to use when you're writing and executing MapReduce jobs, and Java is most common, so it's time for us to start with Java. We're going to drill in and see both how to write a basic word count MapReduce job using Java in Eclipse on Cloudera's VM and how to execute it from that development environment. In this demonstration, I'm going to show you how to write and execute a basic word count MapReduce job on the Cloudera distribution of Hadoop on Linux. Now, to get started with this, we've got to have some input files to work with. So let me go ahead to the training home folder on the desktop and show you the input file that we're going to work with. Again, we're going to go as simple as possible in this first couple of MapReduce jobs and add to complexity as we go through the course. So I'm going to go ahead and open this hello word, and you can see that I have a number of words inside of this file, and we can work with this file initially. So hello word, and this is at the location of the training directory. Now, one of the situations that you can do when you are initially testing MapReduce jobs is you can remove complexity by actually working with just the native file system. And because this is just something I thought was interesting, I thought I would put it into this particular demo. Subsequent demos will be retrieving information out of HDFS and writing it back in. So for this particular demo, we'll do it this way. Now, I choose to write my MapReduce jobs in Java using Eclipse. You can use any of your favorite editors. So what I've done here is I've created a new Java package here, and I've just added the libraries that I need to reference. So there are quite a large number of libraries here. So I've got the Hadoop MapReduce 2.0 from the Cloudera distribution, and then I have the core libraries. I'll just leave this up so you can see all of it. The Cloudera distributions include examples. I have some testing. Then I have some other logging libraries. Log4j is a logging utility. I have an Ant library for build script. I have approval tests for testing, which will come later in the class. And then I have some common libraries as well. And then some more Hadoop libraries. So there's quite a lot of libraries to reference when you first start. So what you want to do is set up a stub project with all the appropriate libraries and then just reference subsequent projects. It's the easiest way to do it. Notice also we have something called Jackson Core, Jackson Mapper. So again, if you're coming especially from the .NET world, this is a lot of new sort of cruft to set up. So you need to have all these various libraries. If you forget a library, you're going to get error when you try to run this. Now most typically you're going to write your Java and then you're going to compile this into a jar file and run it from the command line. But again, just to get us up and running, I've done a little refactoring so I can actually run this from inside of Eclipse. There's several different ways to do it, but again, take my class, you sort of get my way. So let's first drill into this hello world example. I've also put all the implementation into a single file. So I've got the mapper, the reducer, and the job runner in a single Java file. This is not a good production design. This is just for sample code. Normally you have separate files for all these implementations. So I'm going to go ahead and open this up and minimize my Explorer and start going through the code. So you can see inside of here we have our example, and I have nested classes. So I'll just collapse this so you can see sort of a high level of what's going on here. So I basically have a top level class, which is a hello world example, and then I have some nested classes, the map class and the reduce class, which are static classes, and they extend the MapReduce base and the MapReduce base classes. Then I have my entry point, my main, and this is using the MapReduce 2.0 API. A quick check, a way to tell if you're working with that one in whatever samples or whenever you get started, is looking at the import. So in addition to that, I have a little helper run job method. So let's go ahead and actually start with the job runner. What I've done inside of here is I have just created a little utility method which abstracts away the job comp, and I've set my path parameters for my input and output as static values so that I can run from inside of the test environment. Now this is a little sort of a trick, I guess, but I'll share with the audience. Rather than using my HDFS file system, the simplest possible thing is I'll take my input from the actual file system and then I'll put my new output onto the file system. Now we're going to see when we run this it will fail, and it'll be interesting to see if you remember why, and then I'll fix the error. So in any case, let me open up the implementation of the job conf. So you can see I have the two path input output, and here's my job configuration. So I'm running a word count, and I'm setting the output key class, and then the value class, which is an int writable, which is one of my types. And then my mapper class is the map, and my combiner class, which is a local reducer. This runs on each map node. Now again, in this case I don't even really have a map node, I'm just running on the file system, but this is an optimization, it's an intermediate aggregation that we'll be talking about more as the class progresses. We really don't have to have this, but I wanted to put this in the sample code so you would see it. It's very, very common optimization. And then we have the reducer class, we have the input format, which is text input, the output, which is text, and then we have the input paths, and then we just run the job. So this is, you know, pretty self-explanatory. So now let's look at the map and the reduce. So the map takes a long writable type and text, and it outputs a text in an int writable. And what we're going to do is we're going to use a while loop and basically just look for each word in the input and then output the word and then 1, a count of 1 for each word. So that's going to be our key value output. That's all we're doing through the map class. Now the reducer takes those values, the key values, the text and the int writable, and then it will perform an aggregation, basically count up the words, and output a text and an int writable. And you can see this is another while loop, and we just do a plus equals, and then we pass this into the output collector. So I'll leave this up so you have a minute, and this code will be included in the sample code for the class. Now, as I said, when we run this, we'll get an error, and I'll give you a hint. Did you figure it out? The output directory file already exists. So this is a reminder that the output is immutable. So what we need to do is we need to create a new, or actually we can either create a new or we can just delete it, either way. We can go into our file system and we can delete the output directory, and then we can go back into our Java. We can run it. We can see that our MapReduce has a map task running here, and then we can go back out to our file system. We can see our new output directory, and we can see our success message, which is just a file named success, and then we can see our output, which basically counts up our words. So simplest possible implementation. Of course, if we wanted to go ahead and work with the HDFS file system, we would need to load the file, the source file, into HDFS. We could do that using the Hue tool, as I showed in the previous demo, or we could use the Hadoop FS commands. And then for this particular set of code, we could then just go and reconfigure using the HDFS path to our particular node. So if we go inside of our job monitor GUI and use quick links and look at retired jobs, we can see that some jobs were run, but not the job that we just ran. Do you know why? Because this monitors jobs that are run on the HDFS file system. We went deliberately outside the file system, and I did this on purpose because you may use HDFS locally, you may use a cloud implementation, you may use a blob store. So this particular tool is designed to display activity that occurs on your local HDFS. So I wanted to change my input file from hello world to something a little bit longer, this shakepoems.txt, which is, you know, quite a bit longer. It's the works of Shakespeare. I have to make sure to spell it correctly, shakepoems.txt, and then I'm going to go back over to my Java and I'm going to change this to shakepoems.txt, and of course I'm going to have to delete the output because it's immutable, and so I will move that to trash, and then I will go back over here and then run this again. And that's going to produce, there's my map and reduce are done, and I can go back over to my training and look at my output. I got a success, and of course this time I have an entirely different word count. So, and this is just part one of a mini part document because I was able to scale the application of this algorithm that I had written to a much larger file. So this just gives you sort of the introductory thinking around the MapReduce algorithm. You take some input in, you do this first step of processing through the map, and then you do the reducing, which does the aggregation, and you can then scale lots and lots of data against it through the testing. And then of course when you go to implementation, you're going to scale with many nodes and use massive amounts of data.